and welcome to this first video in a series of 3 in which I'll present my PhD thesis titled Orbital Stabilization of Nonlinear Underactuated Systems. So in this video we'll look at the so-called orbital stabilization problem, while in the next we'll look at methods for designing orbitally stabilizing feedback, and in the last we'll look at how we can design robust orbitally stabilizing feedback using sliding mode control. So let's start by answering the question, what is orbital stabilization? So in order to do that, we first have to introduce the notion of an orbit in a mathematical sense. So if we're given an autonomous or time-invariant dynamical system, its state space is Rn, and we assume that the function f on the right-hand side is at least twice continuously differentiable. An orbit of this system is defined as the set of all the points which are traced out by some solution of this system. So for instance, if the system has a solution x star, in the system state space it traces out some red curve, and the set of all the points along this curve is its orbit, which we denote by O. Now the notion of an orbit is often used interchangeably with the notion of a trajectory, but both in this talk and in the thesis I make a clear distinction between the two, in which a trajectory is a curve in time and state space, whereas an orbit is a curve purely in the system state space. So it's the projection of a trajectory onto the state space. Now, since we consider here autonomous systems with a certain smoothness of the right-hand side, orbits of such systems naturally have a few important properties. Since we have local existence and uniqueness due to the smoothness, this means that orbits cannot have likewise, they can be considered as being invariant in some sense with respect to time shifts along them. So this simply means that if we take two solutions, here y and z, both starting on the same orbit, so they trace out the same orbit, but naturally due to the uniqueness of solutions, these points or these trajectories will never intersect one another. Now this last point is also important when it comes to the problem of characterizing the stability of solutions. For instance, it's well known that a non-trivial solution, that means not an equilibrium, it cannot be asymptotically stable in the sense of Lyapunov. This is quite easily illustrated by looking at two solutions evolving upon the oscillator as shown here. So this red and the blue solution, they will evolve upon the same oscillator, but due to uniqueness of solutions, they will never intersect one another. Hence the distance between these 2 points never goes to 0, and thus the solutions are not asymptotically Lyapunov stable. But the stable version of the van der Pol oscillator is known to be attractive. So this motivates another notion of stability, so-called orbital or Poincaré stability of solutions. Now this is essentially just looking at the Lyapunov stability of the orbit of the solution instead of the solution itself. So for instance, asymptotic orbital stability simply implies that for any solution starting in some vicinity of the orbit in question, the distance between the solution and the orbit itself decays to 0 as time tends to infinity. Now, armed with this notion of an orbit of a time-invariant or system, as well as the notion of orbital stability, we can state the so-called orbital stabilization problem. The objective in this problem is as follows. So if we're given a forced orbit of now a controlled nonlinear system, now by forced I essentially just mean that this orbit might only exist in the presence of some nominal control input, then the task is to find some completely time-invariant control law given by some mapping K, such that the corresponding closed-loop system, here abbreviated CLS, is such that any solution of this system which starts within some sort of delta neighborhood of this orbit, the solution will remain within some epsilon neighborhood, and for any epsilon you can find delta, and the distance between the solution and the orbit decays to 0 as time tends to infinity. Essentially what we are trying to do by solving the orbital stabilization problem is to render the corresponding forced orbit an asymptotically stable limit set of the closed-loop system, and notice that the closed-loop system is time-invariant or autonomous, meaning that we have these properties of orbits of autonomous systems. But one might ask, why would you want to solve the orbital stabilization problem? Why not use strategies such as trajectory tracking or perhaps path following? Well, in terms of trajectory tracking, orbital stabilization provides a relaxation of the control objective. So for instance, consider that we want to stabilize some sort of periodic solution. Now in the system's time and state space, this will trace out some sort of spiral curve as shown in red here. In trajectory tracking, we would want to converge onto this curve, or stated differently, we want to track some sort of ever-evolving point, x star, which evolves in the system's state space. While in orbital stabilization, we only need to look onto the projection of this spiral onto state space, which in this case is just this ellipsoid shown here. So this means that if we consider this as an orbital stabilization problem, we in a sense can omit a dimension we need to care about, namely the time dimension, which provides a relaxation of the control objective. So this means that in a sense orbital stabilization is well suited for any tasks in which you do not need a very particular timing of the motion. That is, you do not need to have the states at particular values at very particular time instances. You only need to have a certain synchronization of all the systems as they evolve in time. So you can use this for any type of system, for a robot manipulator, etc., as long as this timing property is not too important for you or for the task you're trying to solve. But it is especially for executing dynamic maneuvers or so-called underactuated systems to which orbital stabilization is particularly well suited. Underactuated systems are systems which have fewer independent controls than they have degrees of freedom, meaning simply that even if some sort of motion might be kinematically realizable for the mechanism, so there might exist a curve in the system's configuration space, there might not actually exist corresponding controls which shapes the corresponding motion, meaning that it might not be dynamically feasible. So for instance, if you have a robot and you want it to perform a backflip, then the available control you have over the system is in midair is quite limited, of course, meaning that you cannot set an arbitrary acceleration upon, say, the center of mass. And this means that even though the center of mass in theory could move in a certain direction, you do not have the available actuators to actually enforce this motion. So in these types of tasks, I show some here as a robot pizziolo and a bit more simplified types of systems considered in the thesis below, and some we'll see in the later videos as well. Now, when you want to solve or try to make such a system execute such a maneuver, then you generally divide the problem into two parts. So in the first, in the motion planning part, you look for a motion which is actually dynamically feasible and which satisfies certain criteria. So perhaps you want it to be energy efficient, avoid collisions, and so on and so forth. Perhaps you solve a trajectory optimization to find this type of motion which has these desired properties. When you find this motion, then you have to design some feedback on top of it. And since we have this limited control authority over our system due to the less independent controls than we have degrees of freedom, this relaxation that orbital stabilization provides is quite beneficial for these types of systems. So in the later videos, we'll look at how we can design such feedback for these types of systems utilizing particular techniques. So hope to see you then.